going down to the river and flying some foiling catamarans, 18-foot or 6-meter catamarans that will, they usually do the true wind speed, maybe a little bit higher than that. So I'll be putting my crash helmet on and flying those this afternoon.
Awesome. Okay. On that note, I'm going to stop sharing my screen and give you access to share.
Yep. And so I'm actually going to stay on video for a little bit and start off with a quick tour of the Cal Lab.
Perfect.
So it's a pleasure to see so many familiar faces. I'm going to pick some names at random, but Ayal, nice to have you. Dasha, see you there. Neil, this is a strange, not really substitute for the meetings that we usually have over the course of the year. And it's nice to be able to do this together, even though we're in the midst of this situation around the world. So I am just outside the Cal Lab here at rbr, and if you see behind me, our Cal Lab is, well, the team is in here at the moment. It's a little bit noisier, so we'll see how the Zoom microphone noise suppression works. The three calibrations that I'm going to talk about today are the main ones that we do here, which are temperature, pressure, and conductivity. So I'll start off with temperature. Here are some of the baths that we use for temperature calibration. These are Fluke or Hart. They used to be made by a company called Hart. Now they're made by Fluke because they're, Fluke has taken over the world. They're not yellow though, unlike most other Fluke instruments. And these are stable temperature baths. They're not particularly accurate, but they're extremely stable to better than a milli-K across the body of water they have. About 7 or 8 liters of fluid that they can manage. You can put all kinds of fluid in them. What we do is a mix of water and methanol. And the reason for that is that we'd like to calibrate your instruments between -5 and 35 degrees Celsius. And obviously, if we were going to take the pure water down, we'd be in trouble at -5. And in fact, even salt water, we'd be in trouble below -2 or so. And so the methanol allows us to do that. It also allows us to calibrate the baths themselves. Actually, I should wind back. We don't calibrate the baths themselves because the reference thermometers that we use, the platinum resistance thermometers, these are actually calibrated in-house to our primary standards. So the 3 primary standards that are most useful for oceanographic work are the triple point of water, the melting point of gallium, and then the triple point of mercury. And so the 3 standards that we have, obviously we need to exercise those to the temperatures, and so being able to do them in methanol means that we can take it down to -40 or so. Our typical accuracy for temperature calibration is 2 millidegrees across that range, but we can do extended points by 5-degree increments up to about 50 degrees. We don't like going further than that. The electronics starts to behave badly, and batteries in particular are not reliable once you hit 60, 70 degrees Celsius. So I have in front of me one of the temperature baths, which is maintaining one of the triple point cells at the moment. But just a moment ago, we pulled out the triple cell here. And so this is the triple point of water. And you may not be able to see the ice mantle that is in there. It's almost entirely filling it up. Next to it, we have our mercury standard. And finally there, we have our gallium standard. Because we've just opened up the tank, we've got a bit of a jump on our temperature readings here. But you can see on our thermometer that we're getting very, very stable results. So this is just being used to calibrate the one of our SBRTs at the moment, but because we've just disturbed it, it's a few micro-K off. So temperature we typically do, I'll tell you more details in a second as we do that. Here is part of our pressure facility. And so we're probably going to have recursive video as one video comes around on the other. We do our pressure calibration in tanks under liquid immersion. However, for up to 2000 dbar, we do it using compressed gas. And so we apply nitrogen to the top of the pressure vessel. So we've got two vessels here. This one is the room temperature one. And this one is the cold tank. You can see some of the condensation on the cap. The test is finished. It's not actually at 1000 dbar anymore. And the reason we actually do a double calibration at both room temperature and about 4 degrees Celsius on our cold tank. And then we also do a full temperature calibration of every pressure sensor from -5 to 35. That's because most pressure gauges are exceptional thermometers, and pressure is almost a secondary measurement to them. So you need to get rid of all the temperature effects first. We also have a deep pressure tank. It's hidden behind this big insulated jacket, and it's under very slight pressure at the moment. So it's actually only under 20 dbar. But this tank will go to 10,000 meters. If you prefer to think in PSI, so 10,000 dbar, 1,000 bar, what is that, 100 megapascals, 15,000 PSI. We try to talk only one unit inside the building because most of them are off by a factor of 10 and cause us a lot of confusion. Wander around and show you some of the calibration tanks that are here. So I'll talk more details about the calibration process later. Igor, would you mind just giving me a hand lifting the lid on one of these? So we have two tanks here, which are both about 700 liters. This is an instrument that's undergoing calibration at the moment. It's just a well-stirred bath with some slight insulation around it, and typically at about 25 degrees. So this is T25S35. And then this tank is much better insulated. It's running at 15 degrees, so it's actually a tank within a tank with a cooling jacket, and we've got a couple of instruments there. Thank you, Igor. And for verifying that we've got constant salinity throughout the day, we've actually got one of our salinometers plumbed up, running permanently in a chiller of its own. So you can just see these slight pipes here, and we pull water samples every so often. So I am going to go find somewhere a bit quieter and start my presentation, and I'll be back in about, well, you'll hear me walking.
In the meantime, I'll entertain by just putting my face on the
you tell a
screen.
funny joke? Warm the crowd up. Go on. You've got to have a funny joke. I think Eduardo's going to come out with a dad joke.
I only come out with dad jokes.
Okay, here's one that Eduardo taught me. This is one of Eduardo's best dad jokes. What's the difference between a good joke and a bad joke? Timing. Right. Now back to our regularly scheduled presentation. Here we go.
Oh, come on. I had one. Okay, go on.
Go on then.
Okay, well, actually, I think this is one that I learned from you. This is one of your best dad jokes, which is, how do you keep a turkey in suspense?
I don't know. How do you keep a turkey in suspense? Boom, boom, boom. Okay, back to calibration at RBR. Dear me, nobody's had a webinar experience like this before. It must be that we're all slightly hypoglycemic, low blood sugar. We might be hypochondriac as well. So I'm going to talk very briefly today really just about the three main calibrations that we do here at RBR: temperature, pressure, and conductivity. We have a big setup for doing dissolved oxygen. We have our own octode that we manufacture, and we have a bunch of wet chemical, fluorometry, turbidity, pH, that kind of stuff. But I'm just going to talk about the quote, big three. So the question I'm going to put out to the audience is, does anybody know what this is? It's funny, you know, on a webinar, nobody wants to jump in and say, I do. And the answer is that this is a form of a Steinhart-Hart equation. And Steinhart-Hart equation is a empirically derived equation that models absolutely beautifully the behavior of a thermistor. And so you can ignore the details like 1 over VR minus 1, because that's really just a way of saying the resistance of the thermistor. Now, we don't actually measure the resistance of the thermistor directly. We measure it compared to another resistor, and so it's called the voltage ratio, and that's why there's a little bit of correction there. But the most important thing is that we have the natural logarithm of the resistance. I'm
going to interrupt for a second. Sorry, are you showing slides? Because we can't see them.
You can't see them at all?
No.
Ah, well, that's, I'm glad you said something. Let's see.
Well, I thought it was part of the joke of the turkey in suspense, but now I realize, no, there.
Okay, how about that one?
Good, yeah, we see that.
Okay, good, thank you. And thanks, Mark and others who chatted to let me know. So that's why nobody understood the equation. So this is a Steinhart-Hart equation, and VR is the voltage ratio because we're measuring compared to a very stable, non-temperature sensitive resistor, and then the thermistor, which is a exceptionally bad or exceptionally large temperature stable, temperature dependent resistor. And so we have the voltage ratio, or 1 over the resistance, the voltage ratio, natural logarithm in there, and then it's the reciprocal of the cube. And so what we're trying to do is to exercise the thermistor under a variety of conditions, as I said earlier, from -5 to 35. We usually do about 6-degree steps, so that makes it 8 steps, 9 steps over that temperature range. And then we do a least squares fit to obtain coefficients for the C0, C1, C2, C3 that you see there. The 273.15 is just the correction from Kelvin to Celsius, as you no doubt figured out. So how do we do that in terms of the instruments that we have? We have these Fluke-Hart baths, which, as I said, they're very stable, but they're not very accurate. We don't actually care about the accuracy of the bath at all, because we're not going to calibrate at exactly 6-degree steps. We're going to calibrate at approximately 6-degree steps, but we're going to measure the temperature very accurately using a standard platinum resistance thermometer, SPRT. So I didn't actually pull out an SPRT to show you while I was in the lab. It was something I meant to do, but I didn't. There are 2 designs that are typically used in this kind of section of the ITS 90 temperature scale. One is using a quartz sheath. Most of our quartz sheath ones are Fluke. And then we have a couple of Inconel sheath. Inconel is a nickel-based superalloy, typically used in aerospace applications. And it's also very stable over time. And stability is the game with an SPRT because you don't want anything to be drifting. You don't want any mechanical stresses. You don't want any strain buildup. And so we use the SPRTs, which are effectively just resistances again, and we put them into the so-called super thermometer, which typically has an accuracy of about 1 part per million. The super thermometer data is streamed into a SQL database, and if any of you have our instruments, you'll have used our software Ruskin. We're a company that believes in making one piece of software do about as many things as humanly possible, and so Ruskin is used in the factory to build your instruments, and it's also used to control the temperature baths. Not only here, because we have some OEM partners who perform their own calibrations, and Ruskin is used to manage their calibration process as well. So all the baths are controlled from Ruskin. All the data from these super thermometers goes into a SQL database. And then the instruments are typically deployed as these 3 are in the photograph, either fully submerged or mostly submerged, with all the measurement bits fully submerged down below. And we do about those 8 points, as I said, 6 degrees separation. And it takes us about 12 hours or so to do a cal. So the tanks are empty during the day because we're prepping for the next overnight run, and usually around 4 or 5 o'clock in the afternoon, they start to fill up with production's output. It takes about half an hour to do the transition of 6 degrees, and then we let them sit for an hour to be completely stable. And we take really just the last minute or so of data from each hour and a half in order to make sure that everything is as stable as possible. I mentioned and showed you some of those primary standards that we use. There are many primary standards, which are materials with intrinsic temperature stability for either a solidification, or usually it's actually the melt point that's used for gallium. The solidification point's a bit complex to determine. Or triple points. And so the triple point of water has this amazing number that you would think is made up. And I don't know enough about ITS 90 to tell you really why it's 0.01000. But obviously the triple point is a much more stable physical parameter than the melting or boiling point. So we use that as much as possible. And we actually check our SBRTs against the triple point every day. And if the SBRTs drift, as they have a habit of doing over time, then once they reach about 0.3 millidegrees off of 0.01, then we correct them again. We do the checks against gallium and mercury every 3 months. They're a bit more laborious, and we don't typically find that there's anything that wasn't found by the SBRT that gets found by the gallium or mercury. So that's really what we're doing, and then doing a fit to those 8 points and that cubic. So you can see that's got sufficient number of points to make a good fit, and assess the residuals. And that is generally the behavior of how we do temperature calibration. Now, you're probably aware that we do temperature calibration of the marine thermistor, of course, because we tell you what the marine temperature measurement is. However, we typically also do 2 other temperature calibrations at exactly the same time that you may not ever be aware of. I have a CTD here, and so here's the CT cell with temperature. This is a fast thermistor. It's a very thin one. Time constant's about 70 milliseconds. We advertise it as better than 100, but it's coming out of the factory. They're usually 70 milliseconds plus minus about 7 or 8 milliseconds. We have a normal thermistor, a standard thermistor. Of course, I didn't bring one today. And that is our moored thermistor, or for long-term use, like on an Argo float. Those are about 700 milliseconds time constant plus minus 10% or so. Those are titanium, so we're quite happy those being in water forever. The fast thermistors are stainless steel. And stainless steel, as you know, in French, inoxydable, non-oxidizable, is a complete misnomer. It's very oxidizable. Well, not very, but it does corrode. And so we don't generally use stainless for long-term instruments which are going to be in the water. However, the conductivity cell also has a thermistor inside it, because we're providing, and you'll see a little bit later, a temperature dependence of the ferrite that is inside an inductive cell. So we calibrate the marine thermistor and the conductivity thermistor that's buried inside. And then, as I was saying, pressure sensors also are very good thermometers. And so we calibrate the pressure sensor with another effectively thermistor. So there are 3 temperature calibrations occurring every time an instrument goes in the bath. Only one of them will ever be stored and read out, but the other 2 are used internally to correct the behavior of the conductivity cell and the pressure cell. So next equation for today, this is pressure, as you can no doubt deduce. And so our C coefficients are those that we use for direct, they're direct coefficients in a polynomial typically, where we're calibrating. We also have X coefficients, and X in our mind stands for cross, which means cross-channel correction factor. So the first equation is that if we just want to make a very simple measurement of pressure, we can calibrate in a single temperature tank against those voltage ratios that I was talking about before using a cubic. And so we do that by a very similar process to temperature. We exercise the instrument under a number of steps that go up from atmospheric to full-scale pressure and fit a cubic to them, usually about 10 steps. One thing that you should know is that pressure at RBR always means absolute pressure. So if you were to take an instrument and take a reading on the desk, it will read at about 10 dbar, which is corresponding to the 1 atmosphere of pressure that's here today. And I'm hoping it's going to fall a little bit and the wind will pick up even further. If you want to use, as is sometimes customary, sea pressure, that is to say the water pressure, ignoring the atmospheric column on top, the logger will do sea pressure correction for you, and you can set a nominal atmospheric value, and it just simply subtracts it, because that's the only difference between absolute and sea pressure. However, it's just a historical tradition here that we've always done it using absolute pressure. This will only give you a pressure measurement that is accurate at the temperature at which that pressure sensor was deployed. And so in order to calibrate it across a range of temperatures so that we can achieve the datasheet accuracy, which is it's about 0.05% of full scale. And so depending on which pressure sensor you obtain, if you're using 20 dbar, it's 0.05% of that. If you're using 10,000 dbar, it scales up accordingly. However, the temperature effects are quite significant. And so we use those 2 tanks in order to exercise the instrument from 0 to full scale at 2 different temperatures. So one is the nominal room temperature, 20, 23 degrees Celsius for people who aren't bilingual. And one is our cold tank, which is usually 2 or 3 degrees. We also then take a measurement of the pressure sensor across the 0 pressure line, or let's say the atmospheric line, 10 dbar, over the full range of temperatures from -5 to 35. So we're in effect building up a 3-sided rectangle that we're able then to interpolate across the middle of. And so you can see that we've got a cubic against the voltage ratio, but we've also got a cubic against the deviation of the pressure that the instrument is running at versus, the temperature that the instrument is running at versus the temperature that we calibrated at in the first place. So that is what these cross calibration coefficients are, x1, 2, 3, and 4. And they mean that we can get 0.05% full scale accuracy across the entire temperature range from -5 to 35. That again is a datasheet number. It's a bit like our time constants. And we like to put conservative numbers on datasheets. When we ship the instruments to you, they're typically accurate to about 0.01% of full scale. But that allows the instrument to have a little bit of drift in that first year over which we say the calibration certificate is valid for. If you're interested, and it's very funny to us, a lot of people are very interested in the accuracy out of the box, and yet a very small number of people, as a fraction, actually keep their instruments calibrated year on year. If you're interested in minimizing the uncertainty of your measurements, you must, either through RBR or through a national calibration lab, get the instruments recalibrated every year. Now, that doesn't mean to say that they drift without bounds. We've done quite a lot of work on drift. Temperature typically over the decades will stay within about 10 millik. So it started off with a 2 millik accuracy, and it will drift about 5 times that level, but it just kind of taps out and stabilizes. Pressure is a bit more drifty, and those figures often occur over the course of a year that you'll see that. So how do we do it? I talked about, I didn't show you the deadweight testers. So we have a couple of deadweight testers as well, and we used to have some of our technicians sit on very, very short stools on the floor spinning weights, and I'm sure many of you have used many hours in your life spinning deadweight weights. However, we have in the last number of years really switched over to using pressure controllers. And at the moment, for instance, a 2000 dbar calibration, we'd use the Mensa 6050 that we have. And it has 4 different quartz-based pressure references inside. So we actually switch the range automatically as we're ramping up. So we start at 10 dbar, we go up 100, 200, so on, 2, 4, 6, 8, up to about 2000 dbar. But different references are used for each of those, and they have this very slightly mind-blowing way of defining accuracy. It's called IS50. And so if you're used to a deadweight tester, the percentage accuracy on a deadweight tester is normally a percent of reading. But we're trying to calibrate a pressure gauge, which is spec'd in terms of percent of full scale. Well, these quartz-based gauges have a specification that is a hybrid of the two. So the IS50 means that for whatever gauge we're using, let's say we're using the 130 dbar gauge, the accuracy of it is 0.01% of reading for the first 50% of the scale, so up to 65 dbar. And then, so that's a line that increases as the reading increases. And then after that, it changes to 0.01% of full scale from 50 to 100%. And so the line goes horizontal. I want to make sure I haven't done, no, I've done it the wrong way around. No, I've done it the right way around. Sorry, I'm trying to draw backwards in my head. We calibrate all of those modules for all of our different pressure controllers every 12 months to NIST standards. And if I just went and plucked the readings for 2019 for the last full year, and the drift on the highest drift that we saw on any of those modules was 0.003%. So quite happy with those and their drift over year. As I said, we're using the pressure controller to pressurize nitrogen. In general, you wouldn't calibrate an oceanographic instrument in a gas, not least because gas is extremely compressible, and so to get up to those kinds of pressures, you're basically building a bomb. So what we do is we fill the tanks with water, and we pressurize only the lines that feed into them. That means that we have a very small volume that we're compressing, and so the amount of stored energy is low. If any of you have ever been to, say, University of Washington and looked at their pressure tank down on, what is it, Northeast Boat Street, you'll see the very ominous warnings about the pressure rating, the pressure level of the tests they're running, and when you need to leave the building. And that's based also on hydraulic compression, because with large volumes of water, the amount of stored energy is still substantial, enough that they have a scale on the wall, which is how high in feet the top would blow if the pressure was released all at once. Thankfully, that's not something that we're too worried about with our smaller tanks. So we do a nitrogen pressure control, but the tanks are actually submersed. And so this performs 2 useful things. One, it means that the temperature variation in the tanks is fairly low for kind of adiabatic effects. And secondly, it means that we can do it quite quickly and also do a leak test at the same time. So we do that temperature calibration first, which is the immersion across constant pressure but variable temperature. And then we do 10 plateaus divided over the full scale. This example's from a 2000 dbar sensor. And 21 room temperature and cold, and then the cubic polynomials. So the temperature correction, we must point out, is applied numerically. It's done inside the instrument itself. We don't use any trimming resistors. Some of you who are familiar with the instrumentation will be familiar with the idea that you can linearize the temperature response using a set of trimming resistors that are supplied, the numerical specifications are supplied by the manufacturer. There's a number of reasons we don't do that. One is that a linear correction is not sufficient. And the second is that it's a very crude technique, and the trimming resistors introduce more errors themselves because they typically have some degree of temperature stability problems themselves, unless you get extremely expensive ones. And so that temperature correction is applied per unit. So each gauge that we ship, the logger knows how to correct the temperature effects on each of them. Finally, conductivity. So conductivity is an interesting one because we use the inductive principle of measurement rather than a contact or electrode measurement technique. And the The way that this works is that we have inside this cell two ferrites arranged one above the other, and they cannot see each other electrically. We take a coil and wrap it around one of the ferrites, and by exciting that coil with an AC waveform, we're able to induce a current that passes through any conductor that's running through the center of that ferrite. And the only conductor that's running through the center of that ferrite, there's none at the moment, would be seawater or water. So the second ferrite is set up in a receive configuration. And so it also has a coil, and it's looking for any AC current that is induced by a changing electric current passing through the center of that ferrite. And so that second ferrite only sees something if there is current passing through the center of the cylinder. And the first one is responsible for driving something through the center of the cylinder. And the coupling, if you're an electrical engineering background, you think of it as an N-to-1 transformer, where you've got N turns on this coil and 1 turn of seawater. And the coupling is given by the electrical conductance of, or resistance reciprocally, of the seawater loop. Because we're interested in conductivity, not conductance, we have to do a couple of things to sort that out. And I'll walk that through in a second. However, the first thing to say is that one of the things that drops out of a transformer-based measurement technique is that the cell is completely linear. That is to say, once you've shown that the cell is linear, and it's linear all the way down to 0, which is to say in air measurements, you can actually calibrate with only 2 points. And if you know it's 0 in air, you can calibrate with 1 point. And you only need a single water measurement or a single conductive measurement to do that. So the simplest measurement here is just deriving these C0 and C1 coefficients for y equals mx plus b against the voltage ratio. However, the conductivity cell has a couple of sensitivities to temperature and pressure. And so one is that the ferrites themselves and the coil assembly behave slightly differently at different temperatures. And that's why we calibrate that thermistor in step 1. And the second is that just like an electrode-based cell, we need to convert from what we can measure, which is conductance, to, in Siemens, if you like, to conductivity, which is Siemens per meter, or as we do it, millisiemens per centimeter. We find it an easier unit to work with. And so we need to establish what is known as the cell constant that converts from conductance to conductivity. So how do we do that? Well, what we do...
Unmute, but that's you, your mic.
Hello, Eleanor Randall. Is it possible you could mute? Great, thank you. Zoom bombing, I'm waiting for people to proceed across the screen not wearing any clothes, but that'll happen later, I'm sure. The way we calibrate conductivity is we start off doing everything in air. We take a resistor set, 8 values ranging from a completely open circuit and then about 47 ohms up to 700 ohms. And that equates to roughly a conductivity of 0 to 90 millisiemens per centimeter. And we're verifying linearity. The reason we're verifying linearity is because it's should be there by design, but if the cell or the electronics are not linear, the rest of the calibration is a waste of time. And so we can do that in air at about 15 degrees Celsius. We then take a single measurement in our 15 degree 35 PSU bath, and that allows us to establish the cell constant, which converts between conductance and conductivity. And then finally, to establish the overall slope temperature dependence, we take a second measurement at T25. However, that temperature dependence of the slope is something that's intrinsic to the unit and doesn't change over time. So you don't need to do that yourself if you're ever recalibrating. You can simply take an air measurement and a single water bath measurement, and that's sufficient. And the corrections that are applied are this internal temperature correction, which is per serial number, And as you can see on the equation, we've also got usually a cubic to compensate for pressure. Why do we need to do that? The reason is that if you're familiar with an electrode cell, the cell constant is actually numerically just the ratio between the area and the length, cross-sectional area and the length of the electrode cell glass tube, as you might see on a seabird, for instance, with platinum electrodes. On an RBR, it is a combination of that, but we also have a current that circulates around the outside. And so it's a geometric factor that incorporates what might be a very non-primitive geometric shape. Instead of just having a pure cylinder, we've got something that's designed for hydrodynamic flushing. So we don't need a pump at all to get water to move through the cell. It's only about 4:1 aspect ratio. But we do have a cell that would not be suited to numerically figuring out what the cell constant is. Instead, by measuring the cell constant, we can establish that for any shape, and that includes if we have any proximity effects from, let's say, on an Argo floating antenna sitting right next to it. However, under pressure, there is still some geometric deformation that occurs, the compression of the cell. And so this pressure dependence factor, the X2, X3, X4, is used to correct the cell for that behavior. Now, it is actually possible, because you can do this with a single point, you can calibrate our conductivity cell at any pressure you like. Now, in a lab, we always do our calibration at atmospheric pressure. But if you'd like to calibrate your sensor at 4,000 meters against a bottle that you pulled from back there, you can absolutely do so. You only need that single point. And that, I think, is really the sum total of temperature, pressure, and conductivity calibration here at RBR. I'd be more than happy to take some questions. I've got no idea whether maybe everybody's hung up by this point, and see where we get to. I think I wanted to say thank you in my last slide. Oh, and my last slide did say thank you to everybody, but yeah, there you go. So
I wanted to say one person hang up.
Oh,
so
really?
I don't know what you said, Greg, but you should find out.
Okay.
There are actually no questions, maybe some comments about our jokes, but no questions on the chat.
Okay.
And I just want to open it now to all the attendees. We have 116, so I'm sure some people have questions. That was definitely a good level of density in your explanations of how everything is derived and the correction parameters. So I'm sure someone has questions. And if not, we're going to start picking on people.
Or telling more dad jokes. I did want to say something fun about, so Dana Swift at the University of Washington has their big test tank there. And I don't have the photograph of it because I didn't ask his permission, but he is about to deploy in a month or so a pair of web floats with firmware written by himself and the University of Washington team in the Pacific, hoping to be Station P. And they did a quick test of salinity in their tank, and they mounted the Argo head on. They mounted two heads on the same on a single dummy housing, and dropped it down. And after it had come to equilibrium, it was very nice to hear back from him that he got readings out of this, not a well-controlled tank, but fairly quiet, of better than 5 millipsu. So that's an excellent result for a non-calibration lab kind of standard. So
excellent. So we are seeing some questions come. James Boyle is asking, can you discuss the drift in the conductivity calibration?
So in the calibration, we don't see drift because we're measuring it at one point in time, but drift over time is something that we, oh, look at that. Yeah, lots of interesting questions there. Drift over time is something that we've done. And I wonder if, Matt, are you on the line?
I am indeed.
Yeah, why don't I share that slide that I talked to you about earlier and see if, do you want to talk to those? So Matt's one of our oceanographers, and he and Mark Halfson, Nick Neslin, going back, Clark Richards, who some of you know, have done a lot of work here at RBR over the years. And there we go. Can that slide be seen, Matt?
Yeah, I see it.
Okay, take it away.
Okay, so I guess the short answer is that, as Greg mentioned, we've been looking into it and characterized the drift over years, and the results are quite encouraging. So I won't go into the details, but basically a few Argo floats have RBR CTDs on it, and we've been using those to assess how the instrument performs over a long period of times, like several years period of time. And so there's a paper that was just submitted to JTech, and that's being reviewed right now, that basically demonstrates that the CTDs don't tend to have a significant drift. There's a very sophisticated way that was developed by the Argo community to assess whether or not the drift in salinity is important, because that's very crucial to be able to detect it and correct for it. And so if you're interested in reading more about it, I will be more than happy to share the manuscript with you to see how we demonstrate. But basically, the bottom line is that the drift over 4+ years for some of those floats, actually, this one is a good example. This one was deployed for about 4 years, and there's no significant drift detected over that period of time.
And this is a float that had a constant offset from the first day. Due to an initial issue, but the drift is not measurable. What we typically find in the calibration lab is that is that it should remain within about 0.01 without any need for calibration at all. Often it's 0.005. Kelso, constant temperature for the lab. No, So we do have the lab as a kind of bubble within the bubble. We're all talking about bubbles these days. And so it's isolated from the external shell of the building. And it has its own air conditioning system, which is nominally plus minus maybe a degree or so. But we don't go to extreme lengths. We have no airlock, for instance. We have 2 different doors into the Cal lab. And we have a saltwater fish tank in there as well. So there's all kinds of stuff going on in there. We don't find that we need to worry too much about that. The biggest reason that NOC Southampton or any other Cal lab worries about it is because they're using a autosal or a portasal. Now, strangely enough, as some of you know, Ottawa is about 2,000 kilometers from the nearest ocean, with equally inconvenient access to all 3 Canadian bodies of salt water. However, the makers of Guildline, the makers of the autosal, are equally poorly situated. They're about 50 kilometers from here, 30 miles away. And so the autosal really doesn't like temperature variations. And if you've ever used one, you'll be aware of how sensitive it is. Often people build a room within a room to house it. Igor Shkvorets, who works here, used to be at Guildline and is very practiced with it, and was actually one of the lead designers on the salinometer that we use, which is our own microsal. It's not available in the market, but it is.
Hello?
Hello there. But it is a simultaneous salinometer. They're not making a sequential measurement, but making a measurement of sample versus reference in parallel. And that means that we don't need to have constant temperature in order to ensure that calibration of conductivity is all up to spec.
So Greg, there was a question also from Sue Hartman on how we do the oxygen calibration, if it's multi-point versus Winkler.
Well, yes and yes. That is to say, so the cal tank for oxygen will take about, what is it now? Somebody on the line can correct me. I think it's about 30 optodes can be calibrated at a time. It is temperature controlled and oxygen saturation controlled. So we have a couple of mass flow controllers and can vary the mix between nitrogen and oxygen and take it from about, I think just with nitrogen and oxygen, we can take it down to close to 5% and up to about 120%. And then we use sodium, I'm about to say metabisulfate, but that's not right. To give our sodium nitrite, to give our 0% reading. Anyway, we have 3 reference optodes that we calibrate directly against Winklers over those conditions. And once we've calibrated them, then we use the 3 of them as transfer standards for subsequent oxygen calibrations. So we do Winklers about once a month, once every couple months. And the reason we have 3 is to look for any drift that's occurring. We do, it would be 49 points overall, so 7 in temperature and 7 in oxygen over that temperature and oxygen saturation range. And then fit, we don't fit Uchida, but we fit something that's close to Uchida for it in order to do the oxygen calibration. Yes, I hope that answered your question, Sue. I see a private question somebody's asked to me from Fernando. Do your pressure sensors have any hysteresis effect in deep deployments? So we verify hysteresis on our pressure sensors, and our accuracy figure is a total error band figure. So it takes into account any kind of error of any, of whether it's hysteresis or nonlinearity outside the calibration equation, that kind of thing. We use 3 different pressure gauges, 2 piezo-resistive ones for the more kind of run-of-the-mill use, like this one. This is a fairly small one in a plastic body, good to 1000 dbar. And then we have a smaller diameter one that's good to higher pressures in our titanium instruments that's good to 10,000 dbar. If you want exceptional resolution or stability, then we use the parascientific digiquartzes. We have our own frequency counting electronics for those, which give about 10 part per billion resolution. That allows you to see, what would that be, 10 micron in water level change from 1,000 meters. It's really quite extraordinary, but let me be honest, the price is quite extraordinary as well. So the piezo-resistive cells are used more often.
Greg, there's also a question from Glenn Sasagawa.
Hi, Glenn.
Could you discuss the effects you have seen with air bubble collapse as hydrostatic pressure is increased? Any time constants?
Glenn, can you expand on the question? The air bubble collapse that we would see on which parameter? In general, the answer is no. The only reason this raises a little bit of flag is that, of course, air bubbles in water do affect conductivity readings, because really it's just a bulk reading of the mass fraction of water versus air. So if you do have a lot of bubbles in the water and, for instance, they adhere to the cell, then you will find that the conductivity reading drops off because the amount of salt water present is smaller by that percentage of gas. However, that typically disappears very, very quickly. And if you're coming up from the bottom, we don't tend to have that issue. If I didn't answer your question, though, please drop in a clarifying one.
Well, he's written at the bottom, pressure readings. We try to purge bubbles from our pressure lines very carefully. But yes, the issue is anticipated at low pressures.
Okay, yes. So indeed, if we are doing an oil-filled line, which we don't typically do. So we do that for the parascientific-based ones. And Glenn is longstanding, for those of you who don't know, has developed several ingenious methods for doing pressure calibration at depth, including a submersible deadweight tester, which is a sight to see. For the Paros, it's always got an oil line, and then we have some kind of either media separator or at least an oil-water boundary. And it's very important to, we find it very important to vacuum the oil to suck any dissolved gas out of it before deployment. And yes, if you see those bubbles, then you do see kind of perturbations in the reading. They can sometimes be large enough on a very thin hydraulic line to appear to cause dynamic effects, which are not there at all, but kind of they're so small, they're large compared to the capillary that they apparently block the line. In our recent BPR0, which uses the A0A technique for eliminating the drift, or largely eliminating the drift in the quartz sensors, we actually use a oil bladder to ensure that the oil is not going to see gas at any time in its life, regardless of kind of diffusion settings.
There's another question. There's another question by James Harding. Are auxiliary sensors, ODO, TU, pH, pressure tested to look for leaks during calibration or before being shipped to customers?
Yes, yes, they are. So the entire instrument is pressure tested. And we want to make sure those sensors on. Interestingly, there's a combination of two things. You want to make sure the sensors work and don't fail themselves, but you also want to make sure that if there's an aperture into the instrument, that doesn't leak. Turbidity these days, we typically use as an MCBH attached sensor. And so if it fails, it only fails because it is mounted on another MCBH sensor that goes directly into the instrument, or it's cabled. Our ODO is also pressure tested. It has a sapphire window, which is good to 7,000 meters. We rate it to, the official rating is 6,000 meters, but I know Crush is well beyond that. So that is checked, but it's also a cabled sensor, so you don't lose the entire instrument. It is atmospheric pressure on the inside, actually a slight vacuum. We pull a vacuum just to keep it dry. Turbidity is actually a solid sensor, and so leaks are not usually a problem unless there's been some fault in the potting process. Same pH is typically for us glass electrodes, and so you are looking to make sure there's no ingress of water into the instrument. Marcus, I see your question about a 1 or 2 point calibration of oxygen. Yes, once the multi-point calibration has been done, as it always is here, then you can do a 1 or 2 point calibration in the field with some known quantity. And an aquarium bubbler is often the most easiest way of doing that, a fish tank bubbler, because you can get 100% saturation very quickly after about, I don't know, John would have to tell me, but I think 10, 15 minutes of bubbling in a small tank. Marcus. Oh, yes, yes. So same question. We submerge the entire, so the Coda TODO, let me see if I can grab one quickly. Murphy's Law is that I don't have one when I thought I had one. So the Coda TODO is a standalone sensor with cable.
Oh, there's Candace showing one.
Sorry?
Candace is showing one.
Oh, look at that. Thank you, Candace. Perfect timing. And so the entire thing is dropped in the water. In her, let's see, our right hand, if she holds it with just one hand, okay, in the hand that she's holding it with is the connector end. The other end is a black, there's the MCBH. And the other end, if she takes this off, she may get wet. This is the protection cap. And she can get a little bit of a vacuum developed on it. And it's Halifax and it's hot and sticky. But there you go. So you can see there the foil on the right-hand side. This foil is quite transparent. That's probably our fast optode with a time constant of about 1 second. On the left-hand side of the image is the thermistor. And that thermistor is actually an oceanographic quality temperature measurement to 2 millik. That accuracy is not required to compensate the foil, but we did it because some people like to get a decent temperature measurement without another proper temperature sensor somewhere else. Yeah.
I think that's it for the questions that were on the chat. Anyone else wants to just turn on your video and your microphone and ask questions?
Well, why don't we actually wrap it up, and I'll say we'll stick around if anybody wants to say hello or just to have a virtual kind of cheers, because I wish it was beer time. It's after 5 o'clock somewhere. But it's great to have so many of you here. See Cecile and Chris and yeah, old friends and new. So thanks very much for coming. Thank you, sodium sulfite. I don't know why I was thinking sodium. I think it's the sterilizer for making beer is sodium metabisulfite. Anyway, thank you, Sue, for the refresher. So we'll wrap up there. Happy to take more questions for anybody who wants to stick around, and hope you all do well. Oh, Kelso, Laura in Havana, you're just rubbing it in. And Oscar, average calibration time, I think we offer 3 to 4 weeks typically for all calibrations. That shouldn't take any longer than that. There's no reason when the system's running smoothly. Oh, there we go. 3 weeks for up to 5 CTDs. It's very funny because one of our members of staff, Krista, who arranges the webinars, shares her login. So I think we have at least 7 Kristas on the call today. But don't be afraid. She's not, you know. What do you call it in German when you're not a doppelganger? You're a 7-ganger. Anyways.
I think Eric Delore, you were going to ask a question. You came online for a moment.
Just waving my hand and saying
Hello.
hi, and thank you very much for that very useful webinar.
You're most welcome. Where are you calling in from?
From the Canary Islands, oceanic platform of the Canary Islands, Blocan.
Yes, indeed. Excellent. Yeah, I don't know whether any of the legatos on the gliders have made it to Blocan yet. Have you seen this one? This is our glider CTD. Optimized for transition, and Blocan obviously is a big glider facility. What's nice about them is very low power consumption because you don't need a pump, and because it's hydrodynamic, you get minimal salinity spiking, which on the electrode-based unpumped CTDs, well, you'll be familiar, the results are not very satisfactory. And I see Liz Creed on the call as well, speaking of glider people. And so, yeah. Kongsberg / Hydroid / whoever they are these days on the sea glider, as well as the Slocums. Those have been integrated, and Ulsimar, and yeah, a couple of other small AUVs.
Mm-hmm. Daryl Adams has a question here. Can you comment?
Hello, Daryl. Daryl, yes. So what we do actually is we calibrate the CTD here at RBR for the glider that it's going to. And we've characterized a number of gliders and their mounting locations. We started doing this with what at the time was the Kongsberg Sea Glider. And so we very uncreatively called it the K factor. And so the K factor is the, so the difference between the CTD in free water and when it's mounted in the body of a glider is a additive factor in salinity. It's just an offset. In conductivity, it's a multiplicative factor. And so the K factor, because it applies in conductivity, is just a multiplier. And it's usually about 1.001, 1.001. I can't remember the magnitude. It's quite small. And the variation from glider to glider is effectively 0. And so we have a kind of standard based, like if you're going to mount it on a sea glider, we'll tell you the K factor for that. If we, and the instrument can take care of it. And so produces corrected results. If you're going to mount it on a Slocum or a Haiyan or what have you. So yes, it is worth us doing the calibration, Daryl, on the glider, but it doesn't need to be your glider. If we've seen one before, we know the K factor for it. Mahalo, Ryan. Great to have you. It's, wow, it feels like it must be an early morning in Hawaii. Guillaume, interesting question. So yes, if we'd been thinking at the start of the Argo program, we would have put a K factor in. However, with gliders, the trick is you want a K factor because you want to take the CTD out, send it back for calibration, and not have any downtime on your glider and just drop another one in. On an Argo float, nobody ever does that. So Argo float CTDs are built onto the head. Usually the manufacturer sends us the head here, or we make the head for the manufacturer and cut the aluminium in Canada. We build it on, we calibrate it with the antenna and the other fittings in place. And then we take the antenna off and just ship the assembly back to the manufacturer. And the manufacturer will then put their own antenna on because the antennas are identical. This means that you don't have to do any other correction. So in effect, the K factor is built into the C0, C1 calibration coefficients. And because you never exchange the CTD off an Argo head without a full calibration in general, we don't need to differentiate between the K factor. Particularly the K factor is helpful if you have a mixed fleet of, let's say, some Slocum and some Sea Glider, and you want to switch the CTD between the two, you just need to set the K factor and off you go. We have two versions of the Legato. So this is the wet bay version, which has an MCBH on the back end. And then we have one, which is the dry bay version, which looks a bit like that, where it's electronics underneath, and you don't need the bottom shell at all. So there you go. We do a couple of different radiuses of curvature on the top as well. So if you're making something like a Riptide, which is a tiny little AUV, about, I don't know, 3-4 inches, 8-10 centimeters diameter, we'll sculpt it properly for you. If you're making a big thing like Sea Gliders, quite a big radius of curvature, then much more gentle curve, just to make sure the hydrodynamics are as good as they can be.
I think that's it for questions that we have, unless anyone else has any other.
Oh, I'm hearing privately that somebody has a Russian deadweight tester in their lab in Cuba, left from 27 years ago. That would be a fun one to lubricate again. Well, let's wrap it up. Thank you ever so much for coming, and it's always fun doing this. I hope it's useful. And don't hesitate to be in touch. If you don't remember anybody else's email address, just write to info@rbr-global.com. And as Candace says, we'll see you all in 2 weeks. If you're on the notification list, or if you weren't on the notification list, write to info and let us know. We'll add you. If you were, then you'll hear another one on the next presentation. Thank you, Anna. Saludos.
Thank you, everyone.
Bye for now.
Good night. Bye-bye.